Should we start? Just a second.
So it's going to be broadcast in Brazil, right? It's 10 in the morning there?
Yes, it's 10 in the morning. Here in Curitiba is a very beautiful day, but cold.
Like almost like here. It's also cold, but
Rafael, is the Brazilian cold?
The Brazilian cold.
Not the Luxembourgish one.
Okay, Brazilian.
No. We have 13 degrees.
15.
13.
13. It's not far, huh? We also have.
Now we are in YouTube. Okay. Then you start this session. I would like to present you. First of all, I am Eduardo Todd from Federal University of Paraná. I would like to present you to Raphaël Frank. He is a professor, senior research scientist at the Interdisciplinary Centre for Security, Reliability and Trust of the University of Luxembourg. He will talk about autonomous vehicles. I think that you can start your talk now. Then, thank you very much. It's with you.
Thank you very much for the introduction. I hope everybody can see me and hear me well. So I'm going to briefly talk about autonomous vehicles and what is the current state of research, and also briefly mention what my research team is doing in that research area. First of all, I would like to acknowledge a little bit the slides you're going to see there. There are slides that has been done from my research team, but also I picked a few slides from different lectures, good lectures, for example, from MIT, from Lex Friedman, or from University of Tübingen. So it's a little bit, to give you a good overview about what is going on in different parts of the world, so that you get a good understanding. So now, maybe before we dive into the technical topic, what is actually the context and the motivation why we do research on, let's say, highly automated vehicle or fully autonomous vehicles? Well, you can see in this statistic that over the last, say, decade, we see that the road fatalities, this is statistics from Europe, tend to plateau. Okay, so we reached actually a level now with the technology in the car where the cars are very secure, where we have a lot of safety systems, but where it's very difficult to go further in let's say, improving those statistics. And one of the reasons is because the main factor of fatalities is the human in the loop and the human error. So it's natural to think that in case we have more automated systems on the road, that we can further improve those statistics. So we have to wait a couple more years to see now if we were right, but that's at least the hope of the community. Before now we go to where we stand today, I think it's always nice to talk a little bit about where we are coming from. And actually, this is not that far in the past, although it's more than 130 years now, where the first car has been patented by Benz at the time, with a maximum speed of 16 kilometers an hour and consumption, an average consumption of around 10 liters per 100 kilometers, which is for today's standard even a high consumption for modern gasoline vehicles. So yeah, that was let's say first attempt, and we know today that a lot of improvement could be made on this particular type of technology. What was also a fun fact is that the first gas station actually was a pharmacy in Germany, because at that time, obviously, there were no gas stations, so you had to get your fuel somewhere, and this was basically an alcoholic solution that was then used as the fuel. So how this developed, and we all know this developed quite quickly, and if we are talking specifically about autonomous vehicles, what is interesting is that, let's say, popular views on autonomous vehicles started already quite early. With one quite known example was the Phantom Auto, where you also have the reference here to get more information, which was basically a car that they said was autonomous. But in the end, it was remotely controlled, and there was actually always a car trailing this vehicle. And in this car, there was a person that basically remotely controlled the vehicle, so that it gave the impression to the outside that the car was actually driving autonomously. Actually, it ended with a car accident where this car basically crashed into another car that was full of reporters, and basically this event then unveiled that the car was not really an autonomous vehicle. But nevertheless, it was interesting to showcase, and already then the public was very interested in this kind of technology. Obviously, the concepts tried to mature over the years, and in 1956, General Motors with his Firebird 2 concept car showed that it could be possible for a car to drive, let's say, autonomously on certain roads. And here the idea would be that inside the road there would be some magnetic kind of wires, that the car could detect and follow, and this way drive partially autonomously on this road. So there's also a video there that you can have a look at. This was a concept vehicle, and it never really made its way now to a commercial as a commercial vehicle. I think that the Firebird in itself got commercialized, but not this particular concept car. Then in the 70s, Peugeot had this Citroën DS, basically using a similar technology, also steered and guided by magnetic cables, and it demonstrated speeds up to 130 kilometers an hour. That was already quite spectacular, because there really we could see that the car was driving completely autonomously. However, it's still a guided technology that requires to have a specific infrastructure, in this case to have specific roads. And I'm not even talking here about the entire perception that is needed so that the vehicle can detect if there's a car in front or behind, or pedestrians and so on. This was basically non-existing. The only thing they showed there is that the car can follow a magnetic stripe on the ground, which was interesting in itself, but was also quickly abandoned due to the fact that having this kind of roads would be just simply too expensive. Let's say the first car or truck that was considered as the first autonomous land vehicle that also used an artificial intelligence, or a very basic neural network, was demonstrated in '88. The project called Alvin demonstrated with a very basic forward-looking vision system that it could imitate human driving. So how did it work? Basically, the AI was trained on human driving performance, and we then fed into a neural network an image of the street and also the turning angle of the wheel. And this has been, for this particular concept vehicle, discretized in 45 bins, defining certain turning angles. And the idea would be to have a neural network that could then predict, by looking at an input image, what would be the appropriate steering angle to apply. These are concepts that still I investigated today. I mean, we're talking here about supervised, classical supervised learning problem, but here it really pioneered because that was in the 80s with a technology at the time that nobody knew, a new network that these days are very used in the context of deep learning. And this proof of concept showed to work fine on the drive of 90 miles on speeds up to 70 miles per hour. This was a project financed by the army, so it was again more a conceptual vehicle that has not been commercialized. So now, beginning of the 2000 came the era of the big challenges. The most popular being the DARPA Grand Challenge. So the first competition was organized in the Mojave Desert in California in 2004 on a route of 240 kilometers, where the DARPA, so it's also an army funded association, then specified this track and offered a prize of $1 million for companies or universities that would participate and successfully navigate the entire track. No traffic, it was only on dirt roads, and the GPS coordinates were also given. So at that time, no one of the robots that participated there finished the round. The Carnegie Mellon University traveled the farthest distance by completing 11 kilometers, almost 12 out of the 240. So we're quite far away, but lots of lessons learned during this kind of very practical events. Now, in 2005, the second DARPA Grand Challenge has been organized, only limited to US participants, and this time 5 teams finished on a route of 212 kilometers with a prize money of 2 million euros. The first was the Stanford team with a little bit less than 7 hours, and still Carnegie Mellon University second with 7 hours and 5 minutes. So now we already got to a point where everybody got excited and say, okay, listen, this is fine. We could navigate on quite difficult roads for a long distance. So what is next? The obvious next step is to put the vehicle in more structured environments, like urban environments where we have certain rules, where we have roads, where you have to obey to traffic law, where you have to negotiate and avoid obstacles and also merge into traffic. Here the route was a bit shorter but more complex, 96 kilometers, urban driving on an abandoned Air Force base, and the price was $2 million. And 11 teams here received $1 million in funding for their research, and the winner was this time again CMU first, finished 4 hours and 10 minutes. Stanford Stanley in second place, 4 hours 29. And there were no non-US participants, although this time it was open for international participants, but the logistics made it very difficult for example, European or Asian teams to join this kind of challenge, which is a pity. So some people said at that time, 2007, okay, autonomous vehicles are there, right? We cracked it. We have vehicles that successfully can drive in complex urban environments. So now, what's next? Let's try to commercialize it. Then, and you might have heard of Waymo, which is a company from Google, always called before Google self-driving cars, and then it was renamed to Waymo a few years back. And I will play this video, and you will probably see it and hear it. Otherwise, you also have the source underneath. I will now play it for a couple of minutes. I might jump a little bit so to maybe to points in the video that are more interesting, but just for you to see a little bit where we stand today with Waymo, which is commonly known as, let's say, the company that is the most advanced when it comes to full autonomous driving.
We have been doing driverless testing in Phoenix since 2017. We have done it at small scale with a few riders, but early fall we have really begun to slowly and responsibly ramp up this service. They can get matched with a fully driverless car where there is no trained driver in the car at all. We have been at this for over 10 years now on public roads, driven for 10 million plus miles. We have done 10 billion miles of simulation, and the simulation is not only things that we have seen on the road, not only synthetic scenarios we have created, but also situations that we have made more adversarial than what we observe. For example, inserting cyclists and motorcyclists into a scene. And through a combination of multiple methods, we have reached the experience and confidence to be able to do this.
Hi, this is Seema with Waymo Rider Support. I just wanted to quickly welcome you to your driverless ride and let you know this ride will be free. If you have any questions or concerns, you can press the help button in front of you at any time to connect with Rider Support. Do you have any questions for me while I'm on the line?
No, I think I'm just sort of taking in the experience right now.
Okay, great. Well, I hope you have a great trip. And again, the help button is in front of you if you have any questions, okay?
Thank you so much.
We're constantly monitoring data both from the test driver cars, the simulation, as well as our driverless cars and our ongoing variety of testing. Anytime we find information that requires us to revisit a few assumptions, we will always put safety first and take the requisite actions. There are a couple of areas that we had to pay special attention to. For example, when law enforcement or first responders have to interact with a completely empty car. So that's an entire area that we designed and tested, but also collaborated with first responders in the local area. Tested, for example, whether or not we are able to detect all kinds of sirens and flashing lights, but also how a police officer in an emergency can take over the car if they need to.
It was a little bit more of like sort of a classic design problem when we had all of this information and we had to create a hierarchy of that information. So what's most important, and then how does color map to what's most important? And so when we see like nearby pedestrians or cyclists, those are rendered as white sort of laser points on a dark background because the contrast there is the highest and they stand out the most. There were some practical considerations as well. We really want to go for a lean back experience when you're in the car. So we want to make sure that that UI isn't in your face and distracting. And so that's why there's a dark color scheme to it and the colors are a bit subdued. It's taken years really to sort of understand the vast number of scenarios out there where people have different information needs. So I might be going to work in the morning, there's no construction, I'm coming home, there now is a construction site that's popped up, and does the car understand that? Again, we're trying to reinforce the car does understand those changing road conditions. And we've been pleasantly surprised. It's one of the examples, unprompted in our user research, that people often cite. The fact that like, hey, there are 14 traffic cones on the side of the road here, and I can see those in the passenger interface, and they're very impressed that the, again, to that level of detail around what the car is picking up.
Cool.
Okay, I'm stopping here. So there you see one example of a company that is already at a very advanced level of autonomy. obviously, in order to get to this performance level, you need a lot of funding. There have been years and years of research behind that. Many engineers and researchers are working on this project. This also requires a lot of AI and AI training that require a lot of infrastructure that is not, let's say, possible for most companies out there, because it just requires a lot of financial power. Nevertheless, even a company like Waymo has not yet been able to commercialize their service on a wider scale. Why is that? So if we look at this particular example here, the car is driving in, if I'm not mistaken, it's somewhere in Arizona, I think a suburb of Phoenix. I would have to say that this puts it in almost the best case scenario, right? We have very regular grid of roads. We have usually clear and dry weather conditions, and we have, let's say, lighter traffic conditions, maybe than now in capital cities. So now imagine you would take this vehicle and would put it in the city center of Rome, for example, or any other let's say more medieval city. Obviously it would not work. So there are still a lot of cases that these companies have to tackle. Those cases are usually called the edge cases. There have been some in the video where you saw, for example, a guy with a stop sign in the middle of the street, so basically a moving stop sign. So you have to understand that, or the car has to understand that this is a person that has a stop sign and is moving with that sign, and so the car needs to understand this context correctly. And there are many of these contexts that are not always easy to recognize for this kind of technology. So there's still some work to be done. So now if we look a little bit, and this statistic is already a few years old, data is the key. I already said it before. You need companies that have the right financial backing in order to be able to connect all this data, process this data, train the AIs. So we have here a statistic of Waymo that by the end of 2019, I think, was collecting more than 10 million miles of autonomous driving data. And this is, of course, a gold mine, because there you have all these edge cases that you can then analyze and try to make your autonomous system improve upon. But then you also have other companies like, for example, Tesla, that famously, markets its autopilot. In the end, it is not an autopilot in the sense that it's fully autonomous. It's what European manufacturers more call assistance systems that already work quite well, but we cannot consider it a fully autonomous vehicle. Nevertheless, having those systems on commercial vehicles and having them widespread in all kinds of different environments, so not only in a city like a suburb of Phoenix, but everywhere in the world, in modern cities, in more medieval cities, is obviously a gold mine as well, because there we can really collect a large number of edge cases and the data that goes with it. And if we look here, the miles that have been driven with autopilot on, these are statistics here from 2021, we reach already 5 billion miles. So that is just a crazy number, and obviously having this amount of data is very helpful for those companies to also keep a technological lead. I would like to briefly mention these different levels of automation because they are often used, and they are interesting for an and useful for an initial discussion, but they are not necessarily useful for design and engineering purposes. But you have level 0. What is called level 0 is a fully manually driven vehicle with no, let's say, assistance systems. And then you would have a level 5 that's on the other end, which is full automation. That would basically mean that a car drives fully autonomously and there is never an interaction needed by a driver or an operator anymore. Even the video you saw before is more on the level 4, because here we still have situation where the car cannot be driven autonomously, and then you would have an operator that can still be remotely, but still there is a human that would drive the car out of a certain situation. Then we have everything that is in between. We have now let's say the more standard assistant system like lane keeping and adaptive cruise control, which would more fit into the level 1 and 2, and then the more advanced systems like the ones that are in the test now would fit more into category 3, and then all the more experimental vehicles like the Waymo would fit into the category 4. But those categories, as I said, are it's not necessarily very, very strict and set in stone. So it's just to give an idea and to be able to categorize a little bit those systems. And then there's prediction. I mean, one question, the question I get the most frequently asked is when will we see autonomous vehicles on the roads? This comes at every talk. So I already try to answer this question here, so you don't have to ask the question afterwards. And there is no single answer for this. First, you have let's say different people that say different things. You have Elon Musk famously saying that autonomous vehicles should already be there today, right? He made some predictions a few years back that says that in 2020 or 2022, most new cars will be highly automated. It looks today that these predictions were not correct. You have other, let's say, researchers like professors at renowned universities that have a more nuanced view on that, and also look at this more from a policy point of view. That there might be certain environments where manually driven cars will be banned from, and then that at a certain point in major cities you might see fully autonomous vehicles, and his predictions are more on the horizon of 2045. Here I'm talking about Rodney Brooks, professor at MIT. And so you can even have other kind of nuances here. You can discuss obviously about the environments. So you might see the cars driving fully autonomously on highway first, because just environments that are much easier to control. There are less, let's say, unexpected things that can happen there. You can even imagine that there might be dedicated lanes for highly automated vehicles that would even simplify further the navigation of such vehicles, because they could even interact with each other. But then, having fully autonomous vehicle that would drive around the Arc de Triomphe in Paris or somewhere in Rome is still something that might be pretty far away. So we will always, I think, for the next few decades, even have cars that have steering wheels where you can drive the car in situations that are quite tricky. But nevertheless, we will see increasing automation in different environments. And this will obviously, change the way we use and consume mobility. So now I would like to spend a few words on this hype that we that I think now is has a little bit cooled down, but a few years ago, 5 years ago or so, or even a bit more, we had this hype and this massive investment in tech companies. Every other day, you had a new company that raised tens of millions of US dollars to build a fully autonomous vehicle. Here are a few examples: Aptiv, Autonomy, Cruise, Navia. So, different purposes, either last mile or robo-taxis. So that was a big promise there. Everybody promised within 1 or 2 years to have a commercial product out there that could go beyond 50 kilometers an hour and would work in all kinds of environments. Well, it did not really happen. So more recently, and there's a statistic from end of last year, but it seems to continue, is that actually a lot of these companies actually shutting down because they burn tons of money and they cannot deliver their promises. So they start to realize that this topic here, this autonomous vehicle and what it entails is much more complex than most people originally envisioned. So I consider this a little bit as this Gartner hype cycle, where you have this visibility, this inflated expectation that peak at some point, and then you have this delusionment. And usually, once this happens, at some point, when the slope goes up again, you have what is called this enlightenment. And then afterwards, the plateau of productivity comes, where we really then see commercial deployments that make sense. And I think we are now, so I think we reached the bottom of the valley, hopefully, and we will now, hopefully, in the next few years, see some companies that will come up with concepts that for specific purposes, not necessarily work in all environments, but for specific purposes will be quite useful. So now, if we dive into why this is actually so difficult, maybe to shed a little bit of light on this, right? And if we look at the performance of human driving, I think that should be the starting point. And here there are some statistics available that tell us that more or less we have 1 fatality per 100 million miles driven, which is an error rate, a fatality error rate of, I let you read the number, but it's very, very small. And obviously, we only want to have a technology out there if it's better than human drivers, right? So actually, we need to design systems that are quite good. Now, if we look at statistics that are out there, and unfortunately, there are not a lot of statistics that we can use because all of these companies keep those statistics for themselves. So this was still a statistic from Google, a self-driving car. That was before Waymo, where over more than 400,000 miles, they had 341 disengagements, meaning situations where the driver had to take over because there was a safety risk here. Obviously, here it cannot be directly compared with the statistic before because we don't know if that would have led to a fatality. Nevertheless, okay, this statistic that is already now a few years old, but shows you that actually there was still some way to go because human performance, at least at that date, was still far superior than the technology we had in 2015. Why is this so? Because of all the challenges, and some I already mentioned. Weather conditions is something that is really something that plays a big role. If you drive in Arizona again in good weather conditions, then it's far easier than if you would drive in environments where you have snow, heavy rain. Obviously, driving on big open parking lots with no guidance on the floor, and also having cars that do not really follow some rules. Same goes for parking garages and pedestrians that behave irresponsibly, reflections, and emerging into traffic. So that are all, let's say, difficult tasks, and it's difficult for our current technologies to do them well. So how is it usually done? If we're talking about an autonomous driving system, it's usually a layered kind of approach we take there. All starts with the environment we are in. So the car is in a certain environment, and it has to perceive this environment by using perception sensors, cameras, lidars, radars, you name it. So we need those sensors in order to make sense of our environment. And then we also use this data to localize ourselves in this context and do our mapping. And once we have this information, and in addition, we have some information about a roadmap. This can be a roadmap like you have in Google Maps, for example, but more recently, everything that has to do with high definition maps, where we have much more details on the geometric and semantic information of the environment that are used specifically for autonomous vehicles. So together with this information, the car can then, on a computer in the car, can then plan a path and make decisions based on also the dynamic objects that might be around the car. And once these decisions are made, we need to send control signals to the vehicle. And we only have 3 control signals. That is, one is to make the car accelerate, the other one is to make the car slow down, so to brake, and the third is a steering signal. Where do I have to turn? And then this loop starts from the beginning. Okay, and this is an interdisciplinary thing. There's computer vision in there, there's control in there, there is localization problems. So it's really interdisciplinary, and usually you need teams really to work collaboratively on such a project in order to build such a system. Briefly about perception, I mentioned cameras. Cameras is what is now, let's say, the most common perception sensor in the vehicles. Why? Well, because it's cheap, and it's actually it covers quite a wide range of features. We can see textures with cameras. We can really identify what object we're talking about. Is it a car? Is it a pedestrian? It works now relatively well also to see distances, although with just a monocular camera it's still a bit tricky, but with some deep learning the results tend to improve there. But usually it's not enough to only have one sensor. Companies like Tesla, for example, say we believe that camera will be the only sensor that we need. A little bit also like the humans with our eyes. We only use a vision system, a stereo vision system, basically to drive a vehicle. But there are other companies that say we also need other cars also for redundancy purposes, and to also work well in different weather condition and lighting condition. That's why another sensor that is frequently used is a LiDAR. So it's basically a laser that gives you a 3D representation of the environment by generating point clouds. But then in the end, what is really the most useful is to fuse all those sensors together to get a really good appreciation of what is around the vehicle in real time. And then you have these different kind of advanced driving systems that make use then of these sensors. For example, adaptive cruise control that will use mainly radars. You have traffic sign recognition, obviously, with cameras. You can have rear collision detect that are ultrasonic sensors, and so on and so forth. So I am a firm believer that having multiple technologies is very useful and will also improve the safety of the systems. So I'm looking at my watch. I still have a bit of time. I will just very briefly talk about the different sensors as I mentioned them. So the radar is a sensor that is relatively cheap these days, that works pretty well in extreme weather condition, but has a low resolution and cannot really be used for any kind of object detection, but it can be used to measure distances and track objects quite well. On the other side is what I mentioned before. We have the LiDAR. I can run this video here. Actually, we did that with our vehicle. A LiDAR is one or multiple lasers. In this case, it was an OS1 64. So 64 lasers that's mechanical sensor that rotate and scan the environment and generate a point cloud. So it's basically thousands and even millions of points in a 3D coordinate system that can then represent what is around the vehicle, and then we can use all kind of AI and other algorithms to make sense of this point cloud by doing some detections of objects and then even classify and track. So it's quite expensive, but it gives a quite good overview of what happens around the vehicle in a 360 degrees view. If you put it on your rooftop, which is something that on commercial vehicles you don't want to do, right? Nobody will buy a car that has on the rooftop such a strange sensor. So in the end, if it's integrated in vehicles, it will be integrated into the chassis, which will require to have multiple of them, even increasing the price. Good. Then we have a camera system. As I mentioned, camera system also have the big advantage. If I can run the video here. Also have the advantage that we can run lots of computer vision detectors on top. We can do recognition of the lanes. We can do traffic sign detection. We can do car detection, pedestrians. We can see the status of traffic lights. There is lots of different applications that we can do with camera systems. That's why they are actually so interesting. Also, they are not very expensive. They generate massive amounts of data that can be very useful for any kind of training and analysis. The thing is that they are not that great in depth estimation, although I said if you use stereo vision, then it's okay, although for far distances it's still not very good. But there are now new concepts around, for example, mono depth, the paper of Google that tries now to estimate, even with a monocular camera, the distances to an object, and it actually works quite well. But still, it does not work very well in bad weather condition. Even there are different types of cameras now that allow you to have night vision and perform better at low light conditions. But they, of course, also more expensive. Right. So I already said camera versus LiDAR. There are pros and cons to it. I think this gives us the best view, and what I also mentioned previously, sensor fusion is basically what will do the trick. So there are different categories: resolution, range, cost, size, weather conditions. All these factors that you would like to have a sensor that is good in, right? And if you put all these different sensors in, or you have a representation like here, a radar plot, and then you put them on top of each other, you will most probably get to a solution that gives you something for all of these categories. So if you combine radar with ultrasonic, passive visual, and you could also even consider a LiDAR here, you will have a system that will work well for most of the situation. So now, before I finish, maybe a bit about our lab. So it's a 360 lab. 360 Lab is basically a research platform that has the different cars and equipment to run projects that have to do with smart mobility. So it's not only necessarily, strictly speaking, autonomous driving, but it can have to do anything with new technologies that are used by vehicles. And for that, we obviously need compute, we need the sensor, and we also need communication, because communication is a big part of it. Often this broader area is referred to as connected and autonomous vehicles, because the connectivity and the coordination of these autonomous vehicles is let's say a field in itself that has lots of potential to improve traffic flow, to even play a role as a sensor. We have not talked about that, but having communication inside the vehicle may lower the need of perception sensor of the vehicle, because the network itself could provide the information that the sensor would provide. And in this sense, we could theoretically lower the price of those vehicles by shifting the compute and the sensoric to the edge of a network, for example. So we have these two vehicles, a Smart 4.2 that has been modified to basically autonomously send signals to acceleration and braking. But the most recent is a Kia Soul electric vehicle, where we retrofitted a full drive-by-wire system that allows us to really control the acceleration, braking, and steering of the vehicle. And we developed a software that we call a RoboCar. The car is in itself called Junior, but the open source project that we are running on the car is called RoboCar, which is composed of the hardware platform that you see here. So it's basically a drive-by-wire system that we have. We have 6 Seconix cameras, one LiDAR, and high precision localization system, and communication interfaces and computers. And then we have the software, which is an open source project. It's not yet fully open sourced. Parts are open sourced, but the plan is to open source the full project by the end of this year, even including a high definition map and how they can be built. So it's our hope that this can be used as an academic project, for other universities or innovative companies to build their own autonomous vehicles at, let's say, at a cheaper cost, because this platform has been designed in a way that does not require very expensive hardware. Here's a demo we did at the end of last year with this vehicle. It's a fully autonomous driving demo we did here in the city of Luxembourg with the car I just mentioned. In order to do so, we needed to apply for an experimental license to do those tests on public roads, and we did those tests with average speeds of now we go up to 50 kilometers an hour even, but on average we are around 35, which allows us to navigate in the traffic. Okay, so that is quite nice. I can show it here. this is an example of the car driving. Now it's driving 40 kilometers an hour. It's on the Kirchberg area, which is a business district in the city of Luxembourg, and it's relying on a high definition map to do the navigation. And then the sensor rack, which is on top of the vehicle, is then used to do the perception. And the control is then done by the different computers that are inside the car and sent to the drive-by-wire system to make the car drive. And we can navigate different difficulties, roundabouts, obviously detect pedestrians and other cars and stop. So this is where we stand today. We're still working on a more advanced path planner, which is almost ready to be tested, and then the full project with all the perception, path planning, HD map, and the exact specification of the hardware platform will be published. Here it says end of 2022, but it should be 2023. This is a mistake. Okay, so the road ahead. So there's still some work to be done. As I said, somewhere in the middle of the presentation, we now are on the slope of enlightenment. There are still these technical challenges. The devil is in the detail. Edge cases are still something that will keep the companies and the researchers busy for some time. But there are also non-technical challenges. I have not talked about that, but this is a topic in itself. Everything that has to do with the legal framework, infrastructure that is needed, and societal implications, obviously also important. So our overall goal, obviously, is to improve safety and save lives. To come back to the first slide of this presentation, and with this, I would like to thank you and finish my presentation. And if there are questions, please feel free to ask them.
Hi, Raphael. Thank you for your very interesting presentation. That's an exciting tema that all people are questioning about it and thinking the problems and the good aspects. First of all, it's very interesting to see the great evolution that we had from the first DARPA challenge. I think that it was a milestone. Then we started to really try to have autonomous vehicles. And it's interesting to notice that in just 20 years, how it changed from a success rate of 0 to a high success rate. But as you told, the devil is on the details. We know how to drive the car, but I think that it's not so clear how to be sure that the machine is safely driving the car. What do you think about this aspect? I think that the society is concerned with the proof of safety. That is a little bit different from classical engineering.
Yes.
That you have in airplanes, for example. You have a control theory that you can assure that with these wind conditions and so on, that your plane will fly safely. And then since we use artificial intelligence, you can demonstrate that it works, but we don't have tools to prove that it's safe. That's
yeah, I fully get your point, and this is also a very important topic. So there are standards that try to address that. And there are some specific ISO standards very known in the automotive industry called functional safety, where basically the systems need to follow certain certain rules in order to assure that they work safely. And in case that the system would misbehave in a certain way, that there would always be a fail safe. That it cannot be, because we cannot, let's say, formally guarantee that all systems will be safe or produce a safe trajectory or whatever. So you need to have a procedure around those systems that would, in case something fails or is detected that misbehaved, that then there's a procedure in place that would, for example, stop the vehicle safely, or where the system, we're talking about commercial system, for example, that the system simply would not work anymore, okay, and that the driver has to really take over full responsibility.
Yeah. Okay. Yes. Another thing about safety is that maybe we cannot assure that it's 100% safe, but the levels that we can achieve, they are much better than the human levels of safety, because as you show it in the beginning of presentation, we are in a plateau. We are trying to improve the safety in the cars, in the traffic, in the human behavior. We have a lot of systems in the cities also to control the driver's behavior. But anyway, we can observe that it's a difficult topic to improve. Maybe we are saturated. We cannot do it much better with the human drivers. I don't know, but
yeah, I mean, that's also what I think. Obviously, there are still factors like drinking alcohol or other factors that we could for example, ban that alcohol is tolerance 0. There are some countries that do that, not all in Europe. There's still some tolerance sometimes. We could also say that maybe young drivers should not drive at night. Things like that would most probably improve the statistics a bit. But
yeah.
Is that something you want? That's a societal question in the end to be addressed. Technology can afterwards help to fill those gaps by having robo taxis that would drive back teenagers or so that otherwise would have maybe taken the car drunk at night.
Yeah. Well, we have a question of Gabriel Nascarella Ishida. That was a case when the pod stopped at a car and then the autonomous vehicle, well, I can go and start it.
I do not know specifically that case, so for me it would be difficult to comment on it.
Okay, but it's a problem that can happen because maybe it was not so clear in the model of driving what you have to do if you are interacting with policy when you are stopped. Maybe that was some.
Yeah, I mean that depends on a lot of factors. Then is this car, does it have a specific license to operate? Is there a safety driver inside?
Yeah.
Is it now
That's more an administrative problem and legal problem than a driving problem.
Yeah, sure. I mean, there needs to be a framework around it that regulates this.
Another question of Pedro Tricossi.
Yeah, I mean, that's a good question. I mean, those cars usually use state-of-the-art detectors, object detectors, which have many different classes. And this includes obviously also animals, for example. So it can distinguish between a human, for example, and a horse, and a bicycle, and the dog and the cat. But most importantly, it also needs to identify it as an obstacle in any case. Okay, there's always this you can either distinguish, okay, which category is this? Is it a pedestrian? Is it a car or whatever? And let's say it all boils down to say at least it's an obstacle and we have to do something. We have to stop.
Yeah.
We have to go around it. So, I mean, for what we use in our car right now, we have different categories that we consider, and that are the categories that are the most common. And in this case, for us, for experimental vehicle, I have to say we do that in research. We don't have any ambition to do that commercially. We do not distinguish if it's a dog or a cat. In that case, we will see that this is an obstacle. In that case,
Okay.
we will avoid it.
Like a box.
Exactly, it would be a 3D box that you have to go around.
Okay. And another question, Thomas Todd.
Autonomous vehicle we integrate with public transportation, mass transportation as buses. Okay. Yeah, this is also a good question. This goes into the discussion of multimodal mobility, and for sure the public transportation, buses, trains, they can also be autonomous at some point. Is important. What I see how it will develop is that you still need these different types of transportation because they have different purposes. Like the train, they move lots of people from one place outside of the city, for example, inside the city. But you might also have in not too long future something like an autonomous mobility on demand service, where you can a little bit like you would hail an Uber, you hail an autonomous vehicle that would come and pick you up at a certain area and can drop you at a certain area. Okay, but this would be complementary to the other public transportation system. So it will only be used in an environment where it makes sense. I'm sure that buses and trains will still be there, or trams or whatever will still be there in the foreseeable future. So it's the integration of all these mobility modes with a certain intelligence, of course, becoming more autonomous, all the categories, that will make it very efficient.
Okay, another question, Eduardo Souza.
Yeah, that is a good question, and the answer is we don't measure the social impact here. We are focusing so far only on the more technical challenges, but obviously these are important questions. There are some other professors at transportation departments that are more transportation engineering that also look at more societal impact of mobility that might be more competent to answer those questions.
Okay, Mateus.
Yeah, and that's also a quite good question that comes frequently. Yeah, the perception is also a big part of this. So you might remember that a couple of years ago there was an accident of an autonomous vehicle. I think it was an autonomous Uber that killed a person. And there was a technical glitch there that made that the perception system did not rightly detect this person and ran over. It was a person on a bike at night crossing a highway, and this sparked a lot of discussions, and it came to the point where basically Uber abandoned even a few months later the autonomous driving project. First stopped it, and then at some point he said not continuing it. So this is a big part. I mean, this can make companies really stop completely development. I think it's not the only reason why they stopped. There might be other reasons for that as well, but I always tend to see this a bit as also a generational thing. Okay, the new generation that will grow up with highly autonomous systems and robots will accept this kind of technology much easier. So the acceptance will be better with the next generation that maybe persons that have a certain age now, right? So it's something that will come naturally, I would say. And one thing to add here is that you should not assume that an autonomous system will never kill somebody. Okay, that is very unfortunate to say it this way, but those systems will still make errors, and this can there will be some very dramatic situations there. But overall, the system should be safer than human. Today, it's acceptable by society if a human driver kills another human, but it's not yet accepted that a robot car kills a human. But will that change over foreseeable future? I think the perception will change, yes.
Yeah, that's very important what you talk. The society accepts that sometimes we kill other people with the cars. No, the society accepts that. Then, okay, you'll be punished, okay, but it's considered okay. We have to.
It happens sometimes, right?
Yes, it happens sometimes. Okay, exactly. Another point of concern is that these autonomous cars probably will also cooperate among them. For example, in crossings and things like that. And then we have two issues. If we have a mix of high-tech, autonomous and cooperating cars with old, non-cooperating cars, and but the problem is if we have a malware, an autonomous car that wants to make an accident, and if they cooperate with another cars, it can give wrong information to the other cars, trying to provoke, trying to make an accident. No, it's a safe security.
Yeah, of course. And this is a huge research field currently ongoing. There are many researchers that work on these questions, how to make those systems resilient to cyber attacks, how to design them first to do not allow that you actually have a way to get into from the outside into those critical systems. So there are different approaches that can be taken there, but obviously there can always be glitches in the software and in the design that would still allow to do that. So yes, this is something that we have to take seriously. And I'm not sure if you heard. It's already more than 5 years ago. It was a car. I don't remember the brand, but some American researchers demonstrated that they could actually send information to a connected vehicle, a commercial vehicle that you could buy at that time, that would actually, you could turn off the engine of the vehicle while it was driving. Okay, they demonstrated this on the highway, and this is actually quite scary. We also did some tests with some cars here at the university, and found that lots of car manufacturers that still rely on pretty old kind of communication protocols to communicate within the car, and the systems has tons of security issues. And these companies have been adding more and more entertainment and connectivity services. And at some point, if you do not pay attention, and if there is a bridge between those entertainment systems and these more critical systems, then you get into very, very dangerous situations. But nowadays, I think that car manufacturers are really aware of the problem and take it very seriously.
Okay. Gabriel Ishida has another question about signals that humans do when driving.
Yes. Mm-hmm. Yeah, this is true. If, for example, you say, come on, stuff like this, or there was actually also a study by Waymo to see how they could replace that, to communicate basically with with other drivers if there's no driver in the seat, right? So there are some easy things, like you could, for example, honk or have the light that blink, to signalize another car to pass. That is one possibility. Another possibility was, and that is especially true in the US, where they have this intersection with the stops on every side, and where sometimes you do not know who's going first, right? So there they designed the system in a way that the car would slowly enter the intersection, and this way that at some point it will go. So that is a signal by itself. It's not necessarily a hand or a vision, but it's a signal. Okay, it's a signal, like a light signal you would give, or an audio signal. And this actually worked for some specific scenarios, right? That's the cases I know of, at least.
Yeah. I have also a question. Do you see that in the future we'll have these autonomous driving software and systems, hardware also, like we have ABS and electronic stability systems that are very standard among different manufacturers, because it's not so good if we have together a car from company A that is very good in autonomous driving, and the car of car B that it's not so good and make more accidents. Probably we will have to face this question in the future. Nowadays research is okay, very good, that Waymo is better than Tesla, no problem. But if we have all these cars together in the traffic, then it's not good. We have a car that is not so good as the best one, or something like that.
Yeah, so I would not make the distinguish between the brands. It's more the price of the vehicle that
yeah.
Right, you have.
I think it's the safety nowadays, in Europe is not so, because it's mandatory to have a high level of safety in all the cars. But in Brazil, for example, we have cars that don't have electronic stability system. We have this mix nowadays.
Yeah, I mean, if you look at the new cars that come out now, I think that most of the cars now, almost, I guess, every new car would have an anti-braking stability braking system and stuff like that, on airbag. These are really quite standard, and the evolution of those systems, I think, will go in the same vein. I mentioned before that the most expensive models of a brand usually have the most advanced systems that you can have. But nowadays, already entry-level cars of different brands already come with, adaptive cruise control and side or lane assist that basically, work with camera systems, and they're quite cheap, and usually offered in the package, an option package that is quite big. I think this evolution will continue like this. You will get more autonomy for cheaper over time, but it will still take time until the full autonomy will make its way down to entry vehicles.
If you have time for one more question, Mateus, one more question about the algorithms.
Yeah, that's actually also one of the topics that interests me a lot, collaborative driving, and there is a lot that can be done there to improve traffic flow, for example. So I was talking about, for example, adaptive cruise control, which is a system that that detects the car in front of you, and then you keep a safe distance, and this can be done autonomously. But we can also imagine a cooperative adaptive cruise control, that are systems that have already been proposed and designed, where the car also has the information of cars that are further in front, or further behind you or on the side of you. And having this information, the car can better decide on how to adjust its speed in order to fit the traffic flow in an optimal way. And the optimal way can be either to increase comfort so that you don't have to do this braking and starting maneuvers. At the same time, improve safety because it's a less risky situation if you drive smoothly. Reduce your energy consumption, obviously, because if you also drive more smoothly, then you will consume less energy. So here, these are things that or applications that can be done, but it requires a certain penetration. So meaning you need to have cars out there that have this capability so that they can actually work together. And this today, and I did my PhD on that topic actually back in 2010. Okay, on vehicular communications, and I thought at the time, okay, it's imminent. In 2015, most of the new cars that will come out of productions will have V2X capabilities, and then we can build on top of that. Unfortunately, it's not the case due to a few reasons. We'll probably not have the time to discuss that, but one is also the communication protocols. One family of protocols is based on, let's say, the kind of Wi-Fi type of communication, and the other is more based on the cellular type of communication. And there have been a big fight between those community, which should be the standard that the car manufacturers should adopt. Then you get to discussion, we do dual stack and stuff like that. But this, this creates a lot of discussions and problems and further delays actually the deployment of such systems, which is a pity.
Well, okay. We have another question?
Yes, from me. No. So, Raphaël, thank you very much. It was really, really interesting. Like I said, for the other people that work with me in the lab, we are like there in the same floor. Sometimes we don't know very much about the work of our colleagues, and when you see this kind of presentation, it's very, very, very interesting. I have a fast technical question that you can be very brief. I don't go so deep, and one more funny question. The technical one is about the training set. Do you have those training sets, like free training sets for this kind of work? And how much, more or less, how many hours a car needs to use for training? Like how many hours of training data of driving, let's say, the car needs to learn how to drive, more or less?
Okay, this is a tricky question because let's say the current AI technologies we use that are based on supervised learning are more for the perception right now. So to make sense of the environment, detecting vehicles and stuff like that. They are very good detectors these days. So we just use what is existing. We're not even training our own models anymore. However, there exist academic data sets out there that have millions of annotated images that you can use for different purposes if you want to do some tests. And we did that with some of the PhD students in our team. Then there is, this question can also relate to one of the slides I showed in my presentation, and was this Alvin vehicle that was really trained on human driving. Okay, this is what we call either imitation learning or an end-to-end system. And the end-to-end system obviously needs to be trained on massive amounts of human training data. We did a proof of concept with our car on a test track. Look at it as if it would be a race track, for example. That is a closed loop. And we drove it like 10 loops and collected human driving data for 10 loops, one loop being around 1 kilometer or so. And this in itself was already enough to let the car afterwards drive on this particular loop, on good weather conditions with no particular traffic and so on. This worked fine. But if you use this imitation learning technique inside a city, that's a completely different thing, because there the complexity is so huge and tons of different possibility where the car can drive. So in theory, this would mean you need enough training data of every road of a city network and drive it a few times in order to collect the needed data that the system can reproduce afterwards, the right turning angles and everything. And there are a handful of companies that still believe this is the way to go.
Mm-hmm.
But I was at first very, very passionate about this particular area of research because it's academically beautiful to do those tests, but to have a commercial product out of this is really challenging.
Okay, understand. Nice. And the funny question is just: do you think a city? Would you agree with the predictions about 35, 41 in a city of Luxembourg? You think that we are close to have like certain regions of the city with only autonomous cars?
In 45?
45, 50, 45 more or less.
As I'm working passionately on this topic, I would like to tell you yes. If you would ask me when I did my PhD at the time and asked me, is every car going to be connected in 2015 or so, I would also have said yes, most probably. So it's an educated guess now that I will tell you, yes, I think it's going to be the case, but I could be wrong.
Okay, of course. Okay, thank you very much. It was really nice. See you soon.
Well, thank you very much, Raphael, for your presentation. Now I will stop the transmission to YouTube then. Okay.